So we're going to imagine that we have three charges situated in an equilateral triangle, so that there will be a distance between each one. And let's make that distance 0.2 meters all the way around. And the charges will all be the same. So we'll just put a Q inside here to show that all the charges are identical. And we'll give that Q a value over here on the side of, well, let's make it 3 microcoulombs, which is 3 times 10 to the negative 6 coulombs. And the question we want to ask is, well, maybe we'll give them some numbers as well. Let's call this charge number 1, charge number 2, and charge number 3, so we can keep track of who's who. All right? So, the question we want to ask is, what is the net force and of course, we're only talking about electrical forces here. There's no gravity or anything else, so I'll put electrical force in brackets. What is the net electrical force on charge number 3? Charge 3. So this guy right there at the bottom right corner. That's our goal. Now, when you look at the triangle, you can see that if we look at charge number 3, and because all the charges are the same, there's going to be repulsion, right? They're all equal. So if you look at charge number 3, it will be pushed this way. It will be repelled away from charge number 2 over here. So let's call that, for lack of a better thing, the force caused by charge number 2, pushing charge number 3 that way. Got it? Repelled. There will be another force caused by charge number 1. You see up here charge number 1, and it's going to repel this way. So we'll call this force on charge 3 caused by the repelling from charge number 1. So I'll call that F1. So F1 is pushing this charge along the blue line, and F2 is pushing charge 3 along the green line. Now it's true that charge 2 and charge 1 are feeling the same forces, but we're not concerned with them. We're only looking at charge number 3, so we don't care about what's happening to them at this point. So we have two forces. Well, the way we would solve this problem to find the net force is just like we would with any other net force equation or problem. We would write, we want the net force, and we want it to be equal to the force of 1 plus F2 in this case. Now let's also go back and look at our picture and remind ourselves that if it's an equilateral triangle, then we know that all the angles inside the equilateral triangle are equal and they're all 60 degrees, right? Which means this is an opposite angle, so we have a 60-degree angle out here as well, which allows us to define directions for F2 and F1. F2, his direction will be 0 degrees, because he's completely and all moving to the right. And then F1, probably the direction for that, well, it'll be 300 degrees. I'll have to try to squeeze that in here. 300 degrees is my direction for F1, right? Remember, we measure angles from the positive x-axis around this way. So 300 degrees. So what I should do is I should modify this a little bit, and I should include those directions in there to remind myself that these are vectors with directions. F1 is 300 degrees, and F2 is 0 degrees. So I'm going to put those directions right in there. Now we can figure out the magnitudes of F1 and F2 using our equation. The net force then would equal K. Now Q1 and Q3, maybe what I'll do is I'll put Q3 in a different color so we can keep track of where it is. So there's my Q3 right there. And we're dealing with a distance of 0.2 squared. And that is at 300 degrees. And then we're going to have another K, Q. This time it's Q2. It's the force of charge 2 on charge 3, which is Q3, divided by, again, 0.2. The distances are the same, squared. And this is at 0 degrees. So what we'll do, because we have two sort of equations here, we know that the values of these are going to work out to be the same, aren't they? The reason they're going to be the same is because the Q's are all the same and the distances are all the same. So instead of writing all these numbers out twice, let's just do a little but statement, and we'll show that K, Q times any Q, Q squared over 0.2 squared, and we can figure that out, right? Now, if you're studying this later, you might wonder how we got that, so let's do it like this. Q1, Q3 is equal to K, Q squared over 0.2 squared, because Q's are the same. And that's also equal to K, Q2, Q3. So all I'm doing here is I'm writing a statement to show that the two values of this and this are both equal to that. And then I can figure that out, and I can, oops, one too many. I can figure that out on the side and then substitute it into my equation. So that would be equal to 9 times 10 to the 9 multiplied by the value of the charge. And if we go right back up to the beginning, I believe it was 3 microcoulombs, was it not? There it is up in the top right corner, 3 times 10 to the negative 6. So that's the number we'll use. 3 times 10 to the negative 6. And there are two Q's multiplied by each other, so we'll square it, and then we'll put the 0.2 squared on the bottom. And then we'll just work out this number, which is telling us the magnitude of the force. So 9 times 10 to the 9 multiplied by 3 times 10 to the negative 6 squared, and then divided by 0.2 squared, comes out to, what I got was 2, pretty much 2.025 or something. Can somebody confirm that? Good. So we know we didn't make a mistake. So that means I can go back up here, and I can put a 2 where this was, and a 2 where that was, and make this a heck of a lot simpler, can't I? So that means my net force now becomes 2 at 300 degrees, and that would be, of course, newtons, 2 newtons, and I'm adding to that 2 at 0 degrees. So now I have to do a little vector triangle, quick, and so I want to do tip to tail. I want to put 2 at 0 degrees. Doesn't matter which one you do first, and the other one is 2 here. Now it's 300 degrees, which means it'll be 60 degrees from here, and that's a value of 2 as well. The angle inside will be 120, because it's 180 minus 60, right? And I'm looking for, of course, the sum of these two, which is this line right here. So I can do very quickly c squared equals a squared plus b squared minus 2 times a times b times the cosine of the big angle c. So this is going to equal 2 squared plus 2 squared minus 2 times, a lot of 2's here, times 2 times the cos of 60 degrees. Nope, sorry, my mistake, the cos of 120. We want the interior angle there, the contained angle, right? Cos of 120. So if we crunch out that number, and someone does it with me to make sure we're all times 2 times 2 times 2 equals negative, and then this will be 2 squared plus 4 equals square root. The answer I got was around 3.5-ish. Somebody else get 3.5 on that? Crunch it out and let me know. Seems about right.
So
3.5.
both angles just be varies since it equals like angle 2.
These angles here and here?
Yes, they both vary since
Yes, they will be, yeah.
one has to be very down because under the angle.
Yeah, we'll get to that in a minute.
Okay.
Yeah. Well, you're asking about these, the two angles here and here. We'll get to those in a second when we figure out the direction for the green line. But first we've got a value of 3.5. Okay? Now you could, if you had to, you could go to a sine law here, right? And get your angle. But because we're dealing with a nice isosceles triangle, as Brandon was pointing out, all the angles in the triangle have to add up to 180. And these two angles in each corner, here and here, obviously have to be the same. So that means that the sum of them is 60, so each of them by themselves is 30. So we really don't need to do the sine law. You could do it and work it out, but we can do it simpler by using the isosceles triangle, which means that the answer is the net force. And if we continue on from what we had written up here, remember all the triangle stuff was to do this addition, so we just replace this. F net now equals 3.5 newtons, and the direction of the 3.5 newtons is 330 degrees. And the reason it's that is because we measure from here all the way around to there, right? And that represents the net force acting on charge number 3. Now that's pretty straightforward. Let's go back to the problem and look at some of the variations that might happen, okay? One of the things that could happen is that the charges might not all be equal. So if you were doing that, let's draw a couple of pictures just to show how this, when you study this question and you look at all the different options, here's what could happen. Well, you could have 3 different charges. You could have 2 microcoulombs here, and 4 here, and 6 here, right? That would simply mean that you would have to calculate different forces. The repulsive force along this line would be bigger than the repulsive force along this line. This one would be smaller. So you wouldn't have an isosceles triangle and you have to deal with it with sine law and so on. But you could easily do that and still tip the tail. So that's one of the things that, could change. The other thing that could change is, what if the charges were not all positive or all negative? What if you had a negative charge here, a positive here, and a positive here? Well, now, this charge would be repelled by the positive charge on the other side in this direction. But instead of being repelled this way, like we were before, it would now be attracted by this force, and you'd have a different triangle when you put these two vectors tip to tail to add them up. So that wouldn't change. It would change your triangle a bit, but the solution could still be found using the same sort of situation. So you could have different charges. The other thing is, you could also have a triangle that's not, a charge here, a charge here, and a charge there. Maybe it's not an equilateral triangle or an isosceles triangle, but then again, that just means your distances will all be different. And so you have to just account for that. But nonetheless, no matter what, you're basically doing a couple of things. You're figuring out the magnitude of the force, right? Using F equals K Q, K Q1 Q2 over R squared. That gives you the magnitude. And whatever R you have to put in there, and whatever Q's you have to put in, you put in. And then you have to consider the direction of those forces. And you do that not by looking at pluses and minuses so much, but thinking about the laws of opposites attraction and like charges repelling. So you can figure out the direction, repelling it against 2L. And then lastly, you're doing a vector triangle, tip to tail, right? If it's an addition. It could also, I suppose it could be a subtraction if you were given the net force. But either way, it's a vector triangle, tip to tail or tail to tail, and you're solving it. And that's how you would deal with a question like this. And we'll stop this one so that we can do another example in a different video.